Hello everyone, and welcome to this evening's webinar on Mathematics Methods Foundation. In particular, this is aimed at the Tasmanian curriculum for the Methods Foundation TASC 3 course. I plan on running through a few exam paper questions and looking at how to do the solutions to those quickly and effectively on your graphics calculator. So let's jump into the first question here. These are all past exam paper questions, and let's have a look. So the first one here is it's asking us to apply the remainder theorem when that polynomial is divided by x minus 2. I'm going to show you a few different ways to do this. Now, normally you would substitute x equals 2 into the polynomial. So let's do that on the calculator. Let's set up a few things first. I'm going to define the polynomial as px. So p function x. Now the defined key is in blue here, just near the number 9. So if you press Control and then the defined key, you get a colon equals. We now need to put in that polynomial, 2x cubed minus 4x squared minus 3x plus 2. Hit enter, and it says it's done. It is locked that into the calculator. Now, the beauty of this is that if I want to recall that polynomial, all I have to do is type in p of x, and it will give me my polynomial back. Now, for the remainder theorem, we need to substitute x equals positive 2 into that polynomial. So if we now do the polynomial evaluated at positive 2, there's our remainder. It is negative 4. Now, another way of doing the same thing, I just want to show you a few different techniques, and it's really up to you to decide how you want to do them, is we can use the polynomial remainder command. If you hit your menu key, go to Algebra, which is number 3, and go down to Polynomial Tools, we want the remainder of a polynomial, option 4 for me. And you get a built-in command on the calculator called polyremainder. There's a few other ways you can access that, but menu algebra is probably the quickest. Now, what you need to do is type in the polynomial. So just to save me typing again, there's the polynomial. We type it in. We then go comma, and we then put in what we're dividing by. We're dividing by x minus 2. So I'm going to put in x take 2. And if I hit enter now, it gives me my remainder. So that's just another way of doing exactly the same thing. Really, it's up to you as to how you want to do that in a quickly and efficient manner. All right, that's question 1. Question 2. We've got a formula there. The velocity of a seismic wave is given by that formula. Find the velocity. So we're trying to figure out what v is, given those various parameters. Now, this really is just a matter of you typing that into your calculator carefully. No special tricks there. So what we want is square root function, and we then need a fraction, and we had k, which was the number 50. So we're replacing k with 50. It was then plus 4/3, so we can go 4 divided by 3, multiplied by u. U was the number 24, all over p, which is 2.7. So just taking you back to the formula here, so k plus 4/3 u over p. We're substituting those numbers into the formula. And we go enter. There is our results, 5.51. Write down your answer. All right, part B, rearrange the equation to make P the subject. Now, obviously, in a test situation, you need to show your setting out as to how you're going to rearrange that equation, but you can use your calculator to check and help you along the way as well. So let's do that. So what we need to do is we need to solve. We're then going to type in the actual equation here. So v equals square root. So solve v equals square root. Once again, we've got the fraction, and it was k plus 4/3 times u divided by p. Now, notice that my p has gone bold. That is because I referred to my polynomial as p. So this is one thing you have to be very careful about, is for me, I cannot use p because I've just used it before. I better choose a different letter. And just for the sake of this, I'm going to choose the letter A. All right. And then I need to go comma A because we're solving for that denominator. So I've typed in my formula. I'm solving for that letter A. And what the calculator will do is it will rearrange that expression, and that's the result that you're going to come up with when you do your algebra. So P, in our case A because P was used before, 4u plus 3k over 3v squared. And it's also telling you that v is greater than or equal to 0, because remember, our equation was the positive square root. So these calculators are pretty smart to let you know that v is still a positive number. All right, so you've rearranged that equation. Question 2, done. Question 3, determine the points of intersection of that parabola and that straight line. So I've got a parabola and a straight line. Once again, I'm going to show you 2 different techniques of how to do this, and it's really up to you to choose whatever you're comfortable with. So the first method I'm going to use is a graphical method, and the second method is we'll do some algebra. So using a graphical method, I'm just going to close these other pages so that we don't get any information from them. Okay, so I now want to add in a graphs page. I need to put in my 2 equations that I've got there. So x squared plus 11x plus 28. So I've got x squared plus 11x plus 28. There is my first parabola. I then hit the tab key to bring up my second function, which is a linear function, 10x plus 40. There is my second function. And I am trying to find the points of intersection of these 2 parabolas. Now I've got 10x plus 40 and I've got x squared plus 11x plus 28. So if I just zoom out a bit, so menu, window zoom, zoom fit is probably a good one. I can see there are 2 points of intersection between my parabola and my straight line. Now I'll just move those labels out of the way. To find those intersection points, we can go menu, analyze graph, and we're going to look for the intersection. I'm going to look to the lower bound and the upper bound, and there is my first intersection point, -4, 0. To get the other one, it's the same process, menu, analyze graph, intersection, slightly to the left of that point, slightly to the right, and there's my second point, 3, 70. So to answer that question there, determine the points of intersection. You can see graphically that they're at -4, 0 and at 3, 70. So let's do a different technique. Control, add page. I'm now going to add in a calculator page. Let's use the built-in calculator command for solving simultaneous equations. So that is menu. It's all under algebra. we are going to solve a system of equations. So it's actually number 7, solve a system of equations. Now you've got two choices here. I tend to always choose the first option there, the system of equations. You could choose option 2 if you know that both equations are linear. But for us, one of our equations is not linear, it's a parabola. So we need to choose option 1. All right, we've got two equations and we have got two unknowns, x and y. So you can change the variables there if you need to. Okay, you literally type in your equations. So the first one was y equals x squared plus 11x plus 28. Second equation, y equals 10x plus 40. The variables are already there. Hit enter and it spits out your answers for you. So x is -4 and the corresponding y value is 0. So that is your pair of coordinates, -4, 0. And your second pair of coordinates, x is 3 and y is 70. That's your second set of coordinates that you can see when we looked at the graphical method also. All right, so two different approaches to solving those equations. Now, once again, you need to show your algebra in an exam situation, but your calculator there is a tool to help you as well. All right, question 4. Everyone's favorite, completing the square. Now, once again, exam situation, you would need to show your steps, but the calculator is very good in giving you a lot of hints and prompts. So let's use the calculator to help us do completing the square on that quadratic. All right, on the calculator here, I'm going to just delete these pages. All right, add in a new calculator page. Now, if you don't know, there is a built-in command that will do completing the square for you. So menu, algebra, it's all under algebra, and there it is, number 5, complete the square. So what we want to do is type in our function, which was 3x squared. So 3x squared, then it was minus 12x, then it was minus 3. You then have to put in a comma x. Okay, you've got to tell the calculator what the variable is, and there it is, it's completed the square for you. So 3x minus 2 squared minus 15. So doing that, it's going to give you a bit of a prompt in an exam as to how to set this up. We now need to do the second part of the question. We've done the completing the square bit. We now need to solve that. All right? So using the solve command on your calculator, we want to solve that expression. So you can just go up and grab it. You don't have to retype it. So you want to solve that expression, and you want to make it equal to 0, and you want to solve it for x. If you hit enter, once again, out pop your two solutions in exact form. Now be aware that the calculator often likes to factorize expressions. So you've got 2 plus root 5. The other one over here is the same as 2 minus root 5 if you were to expand those brackets. So there are your two solutions, 2 plus root 5 and 2 minus root 5. And you've done that by completing the square. All right. Question 5. Find the equation of the cubic drawn. Most of this question you would need to do by hand, but again, we can use the calculator just to visualize a few things for you. So let's have a look at how that function's been drawn. It's got an intercept at -2, and it's got a double intercept because the curve is coming down and bouncing or touching the x-axis at 2, 0. So it's like a double solution. So you've got a cubic there. 2 solutions at 2, 1 solution at -2. And what that y-intercept there at 0, 24 is going to tell us, that's going to indicate our dilation factor. So that's how we're going to find our dilation factor. So if you were answering this in an exam situation, we would have y equals a, which is our dilation factor. Our first root was x equals -2, so we put in x equals +2. So we've got a bracket x +2, because that +2 corresponds to your -2 on the x-axis. Then your 2, 0 is going to be x -2, and we need to put a squared above that because it's actually a double solution. There is your cubic. You now need to figure out what your dilation factor is. We know that the curve passes through 0, 24. So we now need to substitute that into that equation that we have. So we now need to substitute in x is 0, y is 24. This is where you can use your calculator. It's not that difficult to do by hand. But if you want to use your calculator to help solve that, all right, we are going to solve. Our y value was 24 equals a multiplied by, it was then our x value was 0, and where's our function again? +2. So +2, and then we had multiplied by, it was 0 -2, and we were squaring that. And we're solving it for a. So once again, not a difficult equation to solve by hand. We get a equals 3. So that is our dilation factor. And so then our final cubic turns out to be 3x +2, x -2 squared. Now I want to show you a few other features about this question as a bit of an aside. We can use the graphing page. So if I just add in a graphing page, I can type in a multiplied by x +2, which was our first root, multiplied by x -2, which was our second root, squared. Now when I hit enter, the calculator is going to prompt me for a slider, but it didn't. I'm just going to do that again. Just delete my pages here. Okay, start that again. All right, add in my graph page. So I had a multiplied by x +2, and then it was multiplied by x -2 squared. Now, I think I forgot the multiplication signs last time. So note that I've got the multiplication signs in there. We should be okay this time. Yes, I'm prompted for a slider. So if I just hit OK, a slider is basically this movable thing here that we can move around. So if I move that around, you can see how my graph is going to change. Now I'm just going to zoom out a little bit. So menu, window zoom, window settings. -10 to +10 is probably okay on my x-axis. I might go from -20 up to, let's say, +40 on my y-axis, just so I've got a nice window to view there. Move that out of the way. And now, if I move this slider, currently my a value is 1. If I move that slider, you can see what's happening to my cubic as that dilation factor changes. So when it's negative, it gets reflected in the x-axis. As I move into the positives, I'm just dilating that away from the x-axis. Now, if I want to see what this y-intercept is, menu, geometry, points and lines, point on. I'm going to stick a point on this curve at that intersection point there. So all I did was place a coordinate on that curve at the intersection point. And now you can see that if I move that slider, you can see my y-intercept. And when my a value is 3, there's my a value of 3, you can see that my y-intercept is 0,24, which is what we've got on our graph there as well too. All right, so that was a little bit of an in-depth explore of that function there. But ultimately, your solution is as simple as doing that. 3 bracket x plus 2, x minus 2 squared. All right. Next question, question 6. Bit of calculus. Use calculus techniques to determine the gradient of that parabola at minus 2, 17. Once again, I'll show you a few different techniques of doing this question. So let's delete these pages here so that they don't interfere with things. Okay. I am going to draw that parabola as a graph first of all. So my parabola is 2.5x squared minus 3x plus 1. So 2.5x squared minus 3x plus 1. There is my parabola. Let's just resize that screen a little bit. Now, I am looking at the point negative 2, 17. So, if I add a point to that parabola, so menu, geometry, points and lines, I want to place a point on the parabola, so point on. Now, I click on the parabola, and it doesn't really matter where I click because I can change these coordinates. So I'm just going to click right there. And what it's done, it's stuck a point on at minus 1.048. That doesn't really matter. I can now click on that x value and change that to negative 2. Hit enter. It's gone off the page, so I just need to resize my window. So menu, window zoom. I'm going to do a zoom fit. There is my graph. It's probably still a little bit big, so I'll just resize that once more. Window zoom, do a zoom box. Let's go there to there. You can see my point now sitting on that parabola at minus 2, 17. Now remember, my goal is to find the gradient of that parabola at negative 2, 17. If I put a tangent at that point, so menu, geometry, points and lines, I'm going to put a tangent on there. And I click on the curve, and then I click on my point, and it tells me the equation. It tells me the equation of the tangent, y equals negative 13x minus 9. I can see from that that the gradient's negative 13. So the answer to that question should be the gradient is negative 13, because that's the gradient of the tangent line that I've drawn at that point. So if we were to use some differentiation and some calculus now, I'm going to open up a calculator page. Now, to find the gradient of the tangent at that point, I need to do the derivative. So I hit my palette key here next to the number 9, and that little highlighted box there, the derivative symbol, if I click on that, I want to do the derivative with respect to x of my function. Now, I don't need to type it back in again. My function is called f1, so I don't need to type it in again. I can just type in f1 evaluated at x, and that will do the derivative of the function for me. There is my derivative, 5x minus 3, and as you know from calculus, if you look at the derivative there, you get 5x minus 3. I now need to substitute my x coordinate into that derivative. And my x-coordinate is that -2 there. So I've got to substitute that into the derivative. So if I do 5 multiplied by -2, and then add on, and then subtract my 3, there is my gradient. My gradient is -13. And just note that that corresponds to the gradient of the tangent that you've got there as well too. So again, two different ways of looking at that. One graphically, and then that's the typical calculus skills that you do on your exam paper. Derivative, substituting your x-coordinate. All right, so determine the gradient. The gradient was -13. Question 7. For that function, you've got a cubic. Use calculus techniques to find any stationary points and determine their nature. All right, so we've got a cubic. We want to graph that cubic. We want to have a look at the stationary points and decide what type of stationary points they are. Well, let's have a look. I'll clear these pages again. All right, I'm going to do this graphically again so we can see what the graph is. So I'm going to add a graphs page. I need to get that cubic into the graph. So -x cubed. So I'm putting in -x cubed. And then -6x squared. And then +7. There's my cubic. Now it hasn't really fit on my screen very well, so I can just resize that. So menu, window zoom. I'm going to do a window settings. -10 to +10 sounds about right. It's gone off my page a little bit, so I might change that to -20 up to +20. And you can see my cubic, and if I just resize that a little bit more, I've got a nice cubic fitting on my screen now. Okay, let's use the calculator to find the coordinates of these stationary points. Now remember, the stationary point for a cubic here is where our tangent would be horizontal. So we're looking at these turning points. Our stationary points would be those two turning points. So let's find them. Menu, analyze the graph, and I want to look at the minimum. Now the minimum is going to be slightly to the left of that minimum turning point, then slightly to the right. I click, and there is my minimum turning point. Just move that out of the way. -4, -25. To find that maximum, it's the same process. Analyze the graph. I want to find a maximum this time, slightly to the left of that turning point, slightly to the right, and there is my turning point at 0,7. So answering that using a graphical approach, find the stationary points and determine their nature. We can see that there is a minimum turning point at -4, -25. And a maximum turning point at 0,7. So let's have a look at how you do this using some calculus techniques. Open up a new page. Okay, we're adding in a calculator. Now, using calculus, I need to do the derivative again. So I press my palette key. I want the derivative, and I'm differentiating with respect. Now note again, my function is function 1. I don't need to type that cubic in again. I can just use F1. So the derivative of F1 evaluated at x. I need to put the x in there. There is my derivative. Now what I'm going to do is I'm actually going to store that result as a different function. Now the store key, if you haven't used it, is very useful. So if you hit the control key, and just above the var key, you've got STO with an arrow. So if you hit that, you get this little arrow appear on your screen. So that's the store key. And what I want to do is I want to store my answer as d of x. Now for me, the D just stands for derivative. So what I'm doing is I'm storing negative 3x squared minus 12x as d of x. And it says it's done. And that command is now there, that function is now there, and I can recall it when I want to. Now remember, to determine the nature of a stationary point, one way of doing that is looking at the second derivative. So let's do the second derivative. So I now need to do the derivative again, so d on dx, and my first derivative is called d of x. So I'm going to type in d of x. So I am now doing the derivative of the derivative, which is my second derivative. And it tells me that my second derivative is negative 6x minus 12. I am going to store that, so control store, I'm going to store that as dd x, the second derivative. It tells me it's done. So what I did there was I've stored the second derivative as ddx. So we've got the first derivative, we've got the second derivative. Now to find stationary points, we make the first derivative equal to 0. I'm going to show you a new command you probably haven't used before, and it's called zeros. If you type in the word zeros, if I type in 0, it's in italic. As soon as I put a 0 on the end, it jumps upright. That's a built-in command. So if I then put in zeros of my derivative, okay, it is going to return the values of the derivative when it's equal to 0. I'm missing a command because I need to put in comma x. So I've got the zeros of the derivative with respect to x. It gives me a list of the x values where the derivative is 0. So it's telling me it's at minus 4 and 0. Now if you look on the graph, minus 4 corresponds to your x values. So minus 4 and 0 are the zeros of the derivative. Now what I want to do is substitute those two values into the second derivative so I can determine their nature. And the beauty about having this 0 command is we've got a list of numbers. I can now get my second derivative and substitute in those two numbers there. So I'm substituting in my x values to the second derivative to determine the nature of the stationary points. It tells me that when x is negative 4, I've got a second derivative value of 12. And if you know anything about the second derivative, when the second derivative is positive, we have a minimum turning point. When you substitute it in 0, we got an answer here of negative 12. That indicates a maximum turning point. So at minus 4, we've got a minimum turning point, and at 0, we've got a maximum turning point. We then need to work out the corresponding y values. So if I get my function, which is f1, and I substitute in those zeros that we found, there are my corresponding y values. So at minus 4, comma minus 25, I've got my minimum. And have a look at our graph, minus 4, minus 25, there's my minimum. At 0, there's my 0. At 0, comma 7, I have a negative second derivative, so that's my maximum. So I've got my maximum turning point at 0, comma 7. And that's essentially that question done. You've used your calculus techniques using derivatives to find the stationary points, and you've determined their nature. All right, question 8. Very similar question. Use calculus techniques to determine the equation of the normal. So once again, we're doing derivatives, and we're finding a normal this time. So we'll have a look graphically, and then we'll have a look at the algebra as well too. So back to the calculator. So we've got a parabola, and we're looking at the point 2, 5. So deleting these pages. Okay, let's put the graph of that parabola in. Now that parabola was 3x squared, then minus 7x, and then plus 7. There is my parabola. Just move it down a little bit. And we're looking at the point 2, 5. So once again, we'll stick a point on that parabola. So menu, geometry, points and lines, point on. And I want to stick a point on that parabola. And I want to go to 2, 5. So I'm roughly there. I click there. Then I can go and edit that point, change that to 2, hit enter, and it moves it to 2, 5. Move that out of the way. So we've got our point on our parabola. I'm going to put in the tangent first of all. Menu, geometry, points and lines. I want a tangent. And I want a tangent to the parabola at that point. There is my tangent line. And it has given me the equation of the tangent as well, 5x minus 5. I now need to stick the normal through that, which is the perpendicular line. So if I go menu, geometry, points and lines. No, I don't want that one. I think I want construction. So it was geometry, then I want construction, and I want to construct the perpendicular. There it is. So I'm constructing the perpendicular, which is the same as the normal. And if you hover over that little icon, it says click the line and then the point. So I need to click the tangent and then the coordinate, and it gives me the normal that is passing through 2, 5. Now if I right mouse click on that line, on a calculator, right mouse click is control menu. So if you hover over that line and go control menu, which is like a right mouse click, I can choose option 7, which is coordinates and equations, and it will show me the equation of that normal. So that's a graphical answer to that question. The equation of the normal is minus 0.2x plus 5.4. Now it's given to you in decimal form. Let's have a look at how we use some calculus to do this. Okay, so let's add in a calculator page. Now, once again, I need to do the derivative. So I want to do the derivative with respect to x of my function. Now remember that function's already there, so I don't need to type it in. There's my derivative, and I'll get 6x take 7. Now when you look at the question, remember the derivative is 6x minus 7, so that makes sense. I now need to substitute in my x value to determine the gradient of the tangent. I need to substitute in 2. So if I substitute in 2 there, I've got 6 multiplied by 2 take 7. There is the gradient of the tangent, 5. And remember that corresponds to the coefficient of x there, that 5. So there's your gradient of your tangent. You then want the negative reciprocal. So if we do negative 1 divided by that 5, negative 1 over 5, there is the gradient of my normal. So that minus 1/5 corresponds to the negative 0.2 that is there on that line. Now, we need to figure out the equation of the normal. So just opening up a OneNote page here, we've currently got y equals minus 1/5 x plus c. That is the equation of our normal. Now remember, to figure out our c, we need to substitute in the coordinates that our line is going through. So we're going to substitute in 5, 2. So we've got 5 equals minus 1/5 multiplied by 2 plus c. And you can do that very quickly by hand, or you can use your calculator as well. Your constant turns out to be that number there, 5.4. Okay, so there's your constant, 5.4. So your normal then is y equals minus 1/5 x plus your 5.4. Okay, so there is the equation of your normal using your calculus. And again, it corresponds to what you've done geometrically there as well too. All right, that was question 8, finding the equation of the normal. Great. Question 9. I think this is our final question as well. The profit of a company is determined by that cubic expression. X is the number of items produced. And we're looking at 0 to 11, so we're only interested in those particular X values. Use calculus techniques to determine the number of items that will give maximum profit, and what is the rate of profit when we make 5 items per week. All right, so let's have a look at this calculator. I'm just going to delete these pages. All right, I'm going to do a graph first of all, so I can graph that cubic. Now the cubic was -1/3, so -1/3 x cubed plus 5x squared minus 16x plus 2000. There's our cubic. I hit enter. I can't see it because it's off my page due to the size of the numbers. So if I do a menu, window zoom, zoom fit, there is my cubic there. Now it looks a little bit funny, but what I can do is change my window settings to the parameters from the question. So menu, window zoom, let's change our window settings. Now we're only interested, if we have a look at the question, we're only interested between 0 and 11. So if I change my X values to 0 and 11, and then if I change my Y values to say 0 up to 3000, there's a graph there. Once again, it's a pretty flattened graph. I can change my window settings again, so sometimes it takes a few goes to get this right. Menu, window zoom, window settings. Let's go from, say, 2000 to 3000. And we're now starting to see a much nicer graph. Once again, it's still a little bit flat, so I'm going to try a zoom box this time. Zoom box, and I'm just going to go from there to there. There we go, much nicer looking cubic now. So it takes a little bit of fiddling around sometimes to get your graph looking nice on your screen. We're trying to find the maximum profit. The maximum profit is going to occur at that maximum turning point there. So we can look at this graphically. Menu, analyze graph, maximum, and there's our maximum value. It's going to occur when X is 8. So if we produce 8 items, we will have our maximum value. Now, to look at this using some calculus, open up a new page, add in a calculator page. I want to do the derivative. So once again, I'm doing the derivative with respect to x of my function. Now remember, it's called function 1 again. I'm doing the derivative there. There is my derivative, -x squared plus 10x minus 16. I'm going to store that as dx again. So control, store it, and I'm going to store it as d of x. Then I'm now going to solve the derivative equal to 0. So I want the zeros of the derivative, and I've got to put in my comma x, and it gives me 2 answers. Those 2 numbers, 2 and 8, are the stationary points on my curve. The 2 is corresponding to the minimum. The 8 is obviously corresponding to the maximum. Now we would need to prove that the 8 is a maximum. So once again, we could use the second derivative to prove that the 8 is a maximum. And let's quickly do that. If we do the second derivative, of the first derivative. There's our second derivative. And if we now substitute those two x values into that second derivative, I'm going to store that as the second derivative again. There's my second derivative. And so now I've got my second derivative, and I'm going to substitute in those two x values there. And it tells me I've got a plus 6 and a minus 6. Remember, a positive is a minimum. A negative is a maximum. So the maximum turning point, or the maximum profit, is occurring at an x value of 8. And so to answer the question, use calculus techniques to determine the number of items that will give the maximum profit. Our maximum profit will occur when we sell 8 items. And that, again, is corresponding to your maximum turning point there on the graph. And very finally, what is the rate of profit when 5 items are made per week? What we are doing in part B is we are finding the value of the derivative. The word rate means derivative. So what is the derivative when x is 5? And on the calculator, we've already done the derivative. So if I just type in my derivative and substitute in the number 5, because there's my derivative, I sub in 5, my answer is 9. So my answer to the question there is, what is the rate of profit? It is $9 per week is my rate of profit. And that's the final question. So I'll hang around for a few minutes if people would like to post any questions, and I'll do my best to answer them in the last few minutes.